the linear least squares algorithm. And so we saw two things. We saw the application of this to, let's say, curve fitting. Often also referred to as regression. Okay, then what we did is we also developed a theory. How can we use image registration? How can we use linear least squares for image registration, right? So the concept of image registration was, let's say we are given some image over here. So we have another image over here. Okay. So we wanted to know between these two images, what is the rotation, what is the scale, and what's the translation. Translation is like shift in X or shift in Y. You can see this is shifted more. If this is our reference image as an example. Okay, this may be rotated maybe 1 or 2 degrees. It may be shifted, 5, 7 pixels or 10 pixels in the X direction, 5, 7 pixels in the Y direction, right? So anyway, so the question was, how do we determine these parameters? And once we have these parameters, then obviously we can make it align to our reference image and do a better recognition as needed. So our theory was basically, first thing we saw was, for example, if we are given 2 points, so let's say here's the reference image as an example. Okay, if we know the correspondence point, okay, we know how it got rotated. So if we rotate, for example, 5 degrees, this will become, so obviously this point will move somewhere over here or somewhere over here, right? Okay, so from a mathematics point of view, what is our rotation, translation, scaling matrix? So as you guys saw, if this is the point xy, and after we apply the rotation, the scaling, and if this point rotates to this particular point and gets magnified or shifted or whatever, so then if this becomes x prime, y prime. So in the last lecture we developed this theory, x prime, y prime equal to, a, b minus b, a, xy plus t1, t2. So t1 is the shift in the x direction, t2 is the shift in the y direction, right? A, if you recall, was s cosine theta. B was s sine theta, or minus s sine theta. So anyway, we were able to come up with 4 parameters. So A, B, T1, T2 are unknown parameters, which will, if we know them, then if we apply to every pixel in the given image, we'll be able to align it or register it with the reference image. So the question was, how do we determine these? So basically what we did is we set up the equation. We did the summation of all the correspondence points minus x prime, y prime squared, right? Then we did the partial with respect to A, partial with respect to B with T1, T2. We came up with a matrix equation. Once we solved the matrix equation, we were able to get A, B, T1, T2. Okay, so that's one of your assignments, to complete the partial derivatives, set it up as a linear least squares optimization problem. So hopefully, and I gave you the answer already, what the final answer will look like. All you have to do is compute the other 3 partial derivatives and you'll be able to get that answer, right? Okay, so let me show that to you. And then I'll briefly talk about the implementation. Okay, so if I go to the website first, which one? Okay, so let's take a look at our assignment 4, I think it's. No, assignment 4 was just doing it for third order linear least squares for third order system, where you'll be determining the coefficient of A, B, and C and D. So these are the unknowns for this particular data. Okay, anyway, back to your 5th assignment. Okay, so the 5th assignment is basically setting up the cost function, I1 minus transformation of I2. I2 is the incoming image, I1 is the reference image, so that this cost becomes as low as possible. So I gave you the derivative, one derivative, but you have to solve the other derivatives. So this is what the equation, and then once we know the correspondence points, you'll be summing over all the correspondence points, right? Okay, and okay, where did I put it? Okay, so then if you go to the lectures, so if we go to the lectures, oops, what happened? Oh, sorry, it's 15 units. 2015. Okay, so if you go to the lectures, I also gave you a PowerPoint over here. Where did it go? Linear. Okay, so in this PowerPoint, okay, towards the end, okay, this is the final solution to your assignment number 5. So your matrix should look like all these values that you see over here. So anyway, I have not given you these. You have to solve those partial derivatives for the B and the T1 and T2, and hopefully you can verify that it comes out to be this particular answer, right? Okay, so now let me talk about pretending you have come up with all of these equations yourself. So how will we program it? How will we register a given image with the unknown image? So this. Okay, so anyway, let's pretend you're given some image. and you're given another image. Okay, so this is incoming image. And let's pretend we are already given, so in the, our first assumption is that we are already given correspondence points. Then later on we'll remove this assumption and then I'll show you how will we determine that automatically. So given correspondence points between the images. Okay. So what do we mean by correspondence points? For example, it could be the left eye corresponds to the left eye over here. The right eye corresponds to the right eye over here. The nose corresponds to the nose over here. The chin corresponds to the chin over here. Okay. So basically, suppose this is x1 of 1, y1 of 1, x1 of 2, y1 of 2, x1 of 3, y1 of 3, right? So the four actual coordinate locations are given. Of course, the x-axis goes this way, y-axis goes this way, right? And same way over here, if I call this x2 image, so x2 of 1, y2 of 1, x2 of 2, y2 of 2. So anyway, suppose the four corresponding points are given. They don't have to be 4, they could be just 2 points, they could be 10 points, they could be 80 points. Okay, so we'll talk about what if we have less points, what if we have more points, is it better to have less points, more points, and so on. So anyway, our first question is, if we are already given 4 points over here and the corresponding location of the 4 points in the second image, how do we make this same size, same rotation, some translation, so that this becomes, similar to our reference image? So what coding point of view, what do we do? Okay, so let me show you the code. Partial code I've already given to you in the assignment, so I'll clarify that. Okay, so first of all, so remember these were our final equations that you will come up with. Okay. Okay, so if you take a look at these equations, right? Okay, we already know the 4 points, meaning x1 of 1, x1 of 2, and so on, and same way x2 of 1. Okay, so if you take a look over here, for 4 points are given to you. If you plug in those 4 points over here, it will produce a number. Everybody agrees?
Yes.
Okay, same thing over here, number here, number here, number on the right-hand side. So essentially what will this get reduced to is a matrix with 4 by 4 set of numbers. These are our unknowns, A, B,
C,
T1, T2, equal to some set of
4
numbers.
cross 1.
Right, 4 numbers on the right side. Okay, so then to find A, B, T1, T2, what do we have to do?
Inverse the matrix and multiply by that.
Correct. So A, B, T1, T2 is simply, if we did the inverse of this and multiplied it with the right-hand side, then that will be our answer, right? Okay, so I've already given you like a Python code where you can do the inverse through the NumPy library. Okay, because some of the work we'll be doing in C#, so the question is, how do we find the inverse of a matrix? how do we multiply matrices in C#. Okay, so you could write your own matrix class and overload the operators and define an inverse function yourself. But that would be, putting, an effort that we could put into our learning of the algorithms rather than learning how to do the inverse. So there's already a library. I put a link to it. It's called MAPAC, short for Math Pack Library or something. Okay, it already has a matrix class in it, which already has an inverse function in it. Okay. Also, it has already overloaded multiply, add, subtract for matrices. Okay, so very easily. So let me show you the code for that. Okay, so what you will do is you will unzip this MAPAC library. Okay, once you have unzipped the library, you'll create a new project. Okay, for example, in this case, I called it shape transformation, right? Okay, then what you will do is right-click on name of the project, not the solution. Solution is at the top. Right-click, add existing item. Okay, then go to the location of where you unzipped the MAPAC library. Okay, and inside there will be a matrix class. So select matrix.cs. Okay, also select, even though we don't need it, but some of the code in the matrix class is referencing this. So there's another class called QR decomposition. So those two classes, there's one more code over here, LU decomposition. So 3 classes you will need from the MathPack library: LU decomposition, QR decomposition, and the matrix class. Okay, so once they have been added to your project, so you'll see here's the matrix, here's the QR decomposition, here's the LU decomposition. The rest of the code you are writing yourself. Okay, so I'll briefly show you. Okay, so for example, if I created a form, right? Okay, I put a picture box over here. So this is a picture box and a button, and I call this initialize shape. So the idea is, if I click over here, I'll just create 2 sets of 4 points, some random shape like this. Okay, and another shape, something like this. And then I will try to register one shape with the other. Okay. So very briefly, if I show you the code for this initialize shapes. Okay, and as you can see, nothing special over here. Point is a pre-built class, as you already know. So basically, how many points did I pick over here? 1, 2, 3, 4, 5, 6, 7 points, right? And then I added them to a list. This shape 1 is a list. So 7 points have been added to the list. Then I created this transformation class. This is what will, if I go to the transformation. Okay, transformation class is pretty easy. It just has 4 fields in it, A, B, T1, T2. That from the correspondences, by taking the inverse, multiplying by the right-hand side, will determine this, right? So, so basically, just to generate some data, okay, I picked some transformation myself, like 1.05 for the A, 0.05 for the B, and very similarly, shift of 15 pixels, 22 pixels in the Y, right? and I applied to these. Then I randomly picked one of the points and added further 10 more. I also added some outliers. I'll talk about what the outliers are. So think of this as noisy data. Okay. And then here's some code to basically draw them. Okay, so if I run this program, okay, so anyway, this is what the two shapes look like. The 7 points in the blue shape, then I applied a transformation, I picked it myself, and then red shape became the transform, but then I added some outliers, meaning if you take a look at, for example, this point, this is really strange. It really distorts the second one. So this is what we call an outlier. So if we were observing this data, it could be, outlier basically means it's really not a valid data, even though it's showing up in our observations or in our collection of data. Okay, so here's another outlier over here. Wait, this could be actually, may not be the outlier. I forgot which one are the outlier. But anyway, as you saw, I added some outliers there. Okay, so now
Outlier is different from noise?
yeah, so let's say this was the first shape. I'll just pick a simple 3-point example, right? And let's say I have another shape over here. Here's the second shape, right? So as you can see, there's some scale involved, there's some rotation involved. Okay, but what if I have some noisy data? So some other point appears over here. So basically now this becomes something like this. So this is basically an outlier, meaning it was really not part of the data, somehow it showed up, not the real data. Okay. So it's part of the noise. But we don't know which one is noise, right? So basically what will happen now is if for these 7 points, now between blue and red, if we try to compute the AB T1, T2, it will try to align them as best as it can. So you'll see this is what it came up with. Okay, most of the things are pretty decent, except you'll see there's a wide difference over here. I mean, it tried to align, because of this wide difference, it tried to align this, tried to align this, right? So let me briefly show you the code. How do we compute the transformation, like AB T1, T2? So if I go to okay, so as you can see over here, remember transformation was a class with 4 fields, A, B, T1, T2. So that was the transformation class. Okay, so then basically I created another class called ICP transformation, and I forgot why I named it ICP, but anyway. Compute transformation is the method where I give it the 2 lists. The list of 2 points. So if I move it to the next line. Okay, so you can see I give it shape 1, which is a list of 7 points belonging to shape 1, a list of 7 points for shape 2. So then it will try to now compute that matrix where we had the summation. So that 4x4 matrix. Okay, so let's briefly take a look at the compute transformation. So if I right click on compute transformation, go to definition. Okay, and let's see if this makes sense. So on purpose I wrote it in an easy to follow way. Okay, so for example, let's just focus on, as you can see, this loop is going through shape1.count. So if there are 7 things in it, it will go 7 times. There's a plus equal to over here, so it will keep So this is basically doing the summation for the first. And if we go to our math over here, okay, as you can see, was 2x2i squared plus 2y2i squared over the 7 points, right? So basically, shape 2x times x, as you can see, this will make it x squared, correct? Then further 2 will make it 2x squared.
2y.
And then similarly
2y squared.
2y squared. Okay, and then we keep updating it for the 7 points. So same way, once you have the right answer, you'll see basically we are computing 16 values for the matrix. So you'll see here's the top row, second row, third row, fourth row. Okay. Then I assembled all of this data in the A matrix, right? Then can you guess what the B is? See over here, if you take a look, so this whole thing is A matrix in the code I'm showing you. This whole thing over here is the B matrix or B vector. Okay, then to compute this, what do I have to do? A inverse times B, right, as we discussed?
Yeah.
So, anyway, so this is my right-hand side, all the data, again, being accumulated over the 7 points plus equal to, right? And then, because we're using the matrix library, A was declared as a matrix object in the beginning. So all we have to do is just do A dot inverse, and it will do the inverse. And then matrix operators have already been overloaded in this particular library. So if we do A inverse times B, this will be our A, B, T1, and T2, right? So then we obtain it from the result, put it in the transformation with the 4 fields, and return the 4 fields, okay? So once we have the transformation, then what happens to each and every point? In the second shape, each and every point will be multiplied by, so whatever that xy is in the second shape, it will be multiplied by A, B, minus B, A, plus T1, T2. And that point will obviously move to some other point after we apply this computation to it, right? So anyway, back to here. So once we apply, click on this button, now you can see what it's doing. It's passing both shapes to this function. So this will give me what is the A, B, T1, T2 between the 2 shapes. And then basically, as you can see, what I'm doing is I'm applying this transformation to only the second set of 7 points, which will produce, those 7 points will get shifted somewhere else because we're applying a transformation, and then we basically display those. So let's briefly take a look at this apply transformation code. So if I go to apply transformation, okay, and very simple code, as you can see, T times, so we go through every point, right? We pick the x coordinate multiplied by A, y with B, because once again, A, B minus B, A, x, y. So you can see x times A plus B times y, x times A plus B times y, plus T1 will give me the new x value. So I called it x prime. And similarly, this will give me y prime. And then we basically, these were decimal numbers because we wanted to display in pixels, which are integers. And okay, so then we basically return the transformed list of points, and then we display. Okay. Anyway, so once again, if we run it, okay, so this was one data. Okay, this was after we applied the transformation, so as you can see, it's looking a lot closer, right? But because there's some outliers over here, meaning they really were not part of the, they should not be part of the data. So there's some noisy data that got added. You can see there's not a perfect alignment, okay? So our next topic that we want to learn is how to eliminate
The noise.
the noise or the outliers. Okay, so let's talk about what would be a good algorithm. Okay, so let's pretend there are 7 points in the blue shape, 7 points in the red shape. Okay, let's pretend 2 of them are, 2 points are invalid points, or noisy points, or outliers, however you want to think of it. Okay? So one option would be, remember we already have a cost function or a loss function over here, which is basically, let's say x1i or xi, yi, let's call it 1 and 1, minus x2i, or let me make it like this, x1i minus x2i squared plus y1i minus y2i squared. Let's pretend this is our overall cost function. Okay, if the 2 shapes were perfectly aligned, okay, let's say here's one shape. Okay, and even though in the beginning this may be something like this, after we did the rotation translation, then if it is perfectly aligned, this point moves, over here, this point moves over here, this point moves over here, right? It's perfectly aligned.
The loss function.
Then what will be the cost?
0.
0, right? Okay, so one option would be, we don't know which one are the outliers. Our goal is to determine the outliers. Find the cost, okay, between whatever all 7 points are. So let me run it again. Okay, so if I run it again, meaning I click on this one. Okay, so I'm printing the cost. You can see the cost in this case is, it's in terms of pixel coordinates. So 6793.3 is the cost between the 2. Okay, so now 2 points were invalid over here, right? So suppose this is what I do. I randomly remove 1 point from both shapes. So randomly, I pick one of the 7 and I remove it. So 6 points are left. Okay, then based on the 6 points, I compute the transformation, then I compute the cost. If the cost doesn't change,